Hello everybody, I'm Preethi Doss, Microsoft Technical Trainer. Welcome to another session of Azure Roundup. So in this session, I'm going to talk about containers. Let's look at the agenda. So I would spend some time around understanding the difference between virtual machine and containers. And then we will really demystify containers. And then we'll talk about Dockers and Docker images. So let's get started. I want to introduce a character to you, Andy. So Andy is a lead programmer for an application called TailSpinSpaceGame application. So this is a gaming app. Now Andy and team are planning to break down this monolithic application into microservices. So let's say they have two services, web and leaderboard. So the web microservice is implemented in .NET Framework 5 and leaderboard in .NET Framework 4. The amount of compute required for web, let's say, is 1 core, and for leaderboard, another 1 core CPU. Now with this requirement, let's say Andy and team would want to set up the infrastructure on-prem on which the application can run on. So assuming that they would procure their physical servers, let's say Linux server with 4 core CPU and 16 GB RAM. With this configuration, let's look at how virtual machine deployments would fit in. So at the bare metal, we have the compute, storage and network on the host, which is the Linux. And on top, we have the host operating system, which is the Linux, right? And then to enable virtualization onto this hardware, we typically install hypervisor. And this hypervisor, along with this host operating system, divides this physical hardware into virtual resources. So if you create a virtual machine inside this server, the guest operating system that is as part of each of the virtual machine can then interact through the hypervisor to the underlying hardware, wherein the applications running inside those virtual machine can perform system calls to the guest operating system, and the guest operating system would then interact to the hypervisor through its kernel. Okay, so the compute that is required for the application, which is web and leaderboard in our case, as we mentioned, it consumes, like, let's say, 1 core CPU. And then the hypervisor and host operating system would consume another 1 core CPU for running its system calls. Notice that there is guest operating systems sitting right here, which would also consume 1 core CPU, because these guest OSs also run system calls, right? So that consumes some compute power. So the overall compute that is available for the applications to run is limited. So the configurations have already run out. So let's say that Andy would not be able to then deploy both web and leaderboard within the same server, and he may have to procure another server. So the idea is that we want a solution that can optimally utilize the compute, right? Even though Andy has achieved the app isolation, because the web and the leaderboard are both using two different runtime, which is .NET version 5 for web and .NET version 4. The app isolation is taken care by the virtual machine because it provides that isolation boundary. However, we still have to address the compute that can be used by both the applications within the same server. So let's look at how containers come in and solve this problem. We'll consider the same server, the Linux server, which has the bare metal, compute, storage and network. On top, we have the host operating system, which is the Linux. Now, containers are lightweight components that can sit directly onto the host and can interact with the kernel of the host. So let's say we have the web and leaderboard, right? And each is consuming one core CPU, and the host operating system consumes another one core. So we still have room for scale out another expansion or deploying another container inside the same host. So how is that container is able to optimally utilize the compute that's available in the host, plus it is able to solve the problem of app isolation, dependency conflict, all of those are taken care of, right? So how does this magic happen? Then let's get into understanding of what containers really are, right? So to demystify containers, I want to tell you one important aspect, right? What we call as containers are nothing but processes. So what is a process? So let's say I have my laptop, which is a Windows operating system, and I have the kernel, which is the heart of the operating system. So the kernel runs system processes time to time to make sure that the devices are connected to my laptop. Let's say I have a Bluetooth mouse, and there is a device driver that is installed in my laptop. So the kernel would make those system calls from time to time to ensure that the Bluetooth device is always connected to my laptop. So that's an example of a system process. Similarly, containers are nothing but processes that runs on the kernel itself. And these are background processes. Okay. So if containers are really a process, then how does it enable an application to come up and run, right? So where is that environment that is provided for that application to run? So to understand those aspects, we have to introduce two key features of Linux kernel. Okay, so the first one is namespace, and the second one is C groups. So let's talk about Linux namespace for a bit. So by default, every Linux system initially has one namespace. You can think of a namespace as an isolation boundary. All the system resources, such as your file system and your process ID, let's say you have UTS namespace and user. So these are examples of some of the processes that are running within that single namespace. Okay, there is another example that I can say, which is network. So if you want to create additional namespace and organize resources, you could do so as custom namespaces. So by running the process inside the namespace, you are providing that visibility for the process to only access resources inside the namespace. So let me give you more clarity by taking one of the examples of this namespace, right? Let's take file system namespace. We can otherwise call it as a mount namespace. So I've created a custom namespace called a mount namespace here. Okay. I can assign the web process and I can assign the leaderboard process to the same mount namespace. What would essentially mean is that both web and leaderboard process are sharing the file system. Okay. Similarly, I can create a namespace called network namespace. Let's say it's a network namespace, and I can assign web and leaderboard to the same network namespace. And what this would mean is that both web and leaderboard are sharing the same network and they can talk to each other using localhost. So we have the web and leaderboard sitting here and talking to each other using the localhost, and behind the scene it's nothing but they are sharing the same Linux bridge network. And I can give another example of a namespace pertaining to user. So let's say there is another team member in Andy's team. Her name is Mara. Mara does not have root access to the server. However, Mara needs to manage the containers. So what Andy can do is to create a user namespace and provide that user namespace at the scope of Mara's account and have maybe leaderboard process access the user namespace. So Mara would become a root user at the scope of the container, but not at the scope of the host itself. Thereby, you are making sure that Mara has the right permissions, right? So these are some of the examples of how you can create namespaces and have the processes that we call as containers have permissions to access these namespaces. So when they have the namespaces defined, the process would understand only those namespaces and the resources available inside the namespace and nothing else. So with this, we have achieved one level of isolation. What about compute resource? How do we make sure that the web process does not eat up the compute of leaderboard process? So that's where we have C group coming into picture. So C groups provides the process the optimal amount of CPU, memory, network bandwidth, and so on that's required for the application to run. So let's say the web requires 1 core and leaderboard requires another 1 core. So the web process would assume that there is only 1 core CPU that's available in the entire host because it has been exposed only to that 1 core CPU. Similarly, the case of leaderboard. That way, we are making sure that processes don't hog resources reserved for each other, right? I hope this kind of gives you a clarity around what happens behind the scene for a container process. Now let's look at understanding how Andy and team would create these container processes. As it is, it looks a bit complicated, right? Now, should Andy and team be understanding all of these, like going at a host kernel level and creating those namespaces all by themselves? Maybe not, right? There should be a better way of doing it, right? So that's where we have Docker coming in and saving the life, right? So Docker is a container runtime environment or like a software that you can install onto the host. So Andy can install Docker onto that Linux host that he has procured and instruct Docker that, hey, these are the configurations that are required for my processes. You go ahead and interact with the kernel and you prepare these processes for me, right? So Docker internally has two components. One is the Docker client and the other one is the Docker daemon. So Docker client is simply the front interface that you can see. The client instructions are received from the command line interface by Docker client. And Docker daemon is the server that runs in my host all the time that would receive those instructions and perform operations by interacting with the host's kernel. Okay. So let me bring up a diagram here to explain the flow of how Andy and team would go about using Docker for creating the container process. Let's assume we have Andy sitting right here, and Andy would use Docker to build and push what we call as image, right? So before going into image, let me tell you this, guys. So Andy would start writing instructions for Docker using a file called DockerFile. Okay, let's say this is a DockerFile which contains set of instructions that Docker would execute and package that application And this application would eventually be the containerized application that runs on a specific host. So the output of building this Docker file is nothing but a Docker image. So we have two, uh, you know, terms introduced here. One is the Docker file, the other one is Docker image. As I mentioned, Docker is just an extensionless file which contains set of instructions that you are asking Docker to execute to build a Docker image. So if that's the case, what is a Docker image really? Okay, so let's get into details of that. A Docker image is something that you package your application and its environment into. So it can contain the file system and the metadata. So the metadata could be a path to executable that should be executed when the image is run, right? So that's just an example. So let's dig into what image really is, right? So in Docker, images are composed of layers, right? So different images can contain exactly same layers because every Docker image is built one on top of another image, and two images can both use the same parent image as their base. I know it is getting a bit complicated, so let me simplify this. Let's take, for example, Andy is writing Docker file for web service or the web process that we spoke about. So web uses Linux as its base operating system. So just remember this, even though we have the host operating system and container process can run on the host operating system, the application would still require a very lightweight base operating system for the process to have its boot and file system capabilities. So this base operating system, base OS, is going to be a very lightweight OS. So the web also require the runtime, which is .NET version 5. Okay. So these two together will constitute our base image. Okay. So which will be described in first set of instructions in the Docker file. Now Docker will understand that, hey, this base image is already available in a repository called Docker Hub. So what Docker will do is just pull that image and download that image into a specific file system namespace or a mount namespace inside the Linux kernel. Now, if leaderboard service also requires Linux and .NET version 5, what Docker would do is that it would share this file system or the mount namespace for both web and leaderboard. As simple as that. But in this case, we have leaderboard use Linux for base OS. However, it uses .NET version 4 as its runtime. So what Docker would do is make use of the layer within this base operating system, the base image that has the base OS, right? It would share only this component to the leaderboard process. Got it? So behind the scene, everything is like layers, guys. So like how you will, have layers of cake arranged one on top of other, Docker would layer images one on top of the other. So the one image will go for the base OS, the other image will go for the runtime, the third image will go for the application, dependencies and libraries. So in our case, let's say that Andy is still writing the Docker file for the web service. The second set of instructions is to write for the application dependencies, which is the application DLLs, that is executable, and its libraries. So Docker would then convert or execute this instruction and convert that into an image layer on top of the base layer, and it will place the app DLL since it's a .NET application plus its dependencies. Now we have two image layers that Docker has created for the web service. What next? There has to be an environment in which you can run this image to create the application itself, right? So you can use Docker and run this image in any of the hosts that supports Docker. So essentially you would need a Docker runtime installed in any host where you want to run this image as a container process. Okay. So I would like to take you into a demonstration for Tailspin, and let's see step by step of how to write that Docker file and create Docker image, and then we'll get back to this place. So I have with me Visual Studio Code with the TailSpinSpaceGame application project. So it's a .NET project, as I mentioned, which uses .NET Framework 5.0. So what I would do is create the Docker file, right? So let's say that I'm Andy and I'm creating a Docker file for this web service of Tailspin. So I'll start with creating an extensionless file called DockerFile under the source folder. And let me bring up the set of instructions. So I'll start with from. So what this from statement would denote is that I'm using Microsoft.com/.NET/ASP.NET 5.0 as the base image. And this image is already available in Docker Hub. So while Docker is executing this instruction, it will pull that base image, which will contain the base OS and the runtime that's required. We have discussed about that. Okay. And I'm also additionally giving other instructions like, hey, open up port 80 in my container once we have run the container image onto a specific host, right? Let me bring in the other set of instructions. So here is where it gets interesting. I've introduced another from statement, right? And I'm saying from another image, use this as build. What I've done here is I've optimized on my Docker file by introducing something called multi-stage Docker file. So I have another stage called build stage, which uses a base image that has .NET SDK 5.0. Okay, so this is an optimized Docker image that may not contain all that is required for the container. It requires only the necessary software or dependencies that is required to build my application. Okay, so now that I have the base image that's necessary to build, let's look at the next set of instructions. I'm creating a working directory called source. So what Docker does is that for performing this build stage, it would require an agent, like how we have build agents for our CI/CD pipeline. It would create an intermediary container as an agent, and it will create the working directory as source folder. And based on the next set of instruction, I'm asking to copy the project CS project file from my host, which is from my local, my laptop, to that intermediary container that is running as an agent. And then I'm asking Docker to do .NET Restore because .NET framework is available in that intermediary container. It will do .NET Restore by restoring the dependencies. And then I'm saying copy from source to destination, copy whatever is there in the source folder into the destination. Okay. And then I'm doing a .NET build. The output will be the compiled files, right? Let's look at the next set of instructions. So I'm introducing the third stage, which is the publish stage. And if you look at the publish stage, I'm using from build as publish. Okay, so this would mean that use the output of build stage as an input to the publish stage. And the output of build stage is nothing but the compiled source. And I will go ahead and ask Docker to run .NET publish to publish the build artifact. And then the last set of statements is from base to final. Here is what it gets more interesting, right? I'm asking Docker to use the base image from here and then get the output from the previous stage, which is the publish stage, and layer this output, which is nothing but the DLL itself, on top of the base image. That's about it. So what I have accomplished is two image layers, right? One is the base image. The other one is the writable image layer on top. That is nothing but the application file and its dependencies. Thereby, I've optimized this Docker file by not considering the intermediary stages, right? So we have the build compile files, right? We do not require them for the application to run. All we require is the app DLL for the application to run inside the container. So we've got what the container actually needs. We are finally ending it with an entry point, which will simply do a .NET run on the container. It will bring up the application, right? So let's go ahead and execute this Docker file. Docker build -file. You can change the name if you want, or you can retain a DockerFile. The default is DockerFile, but if you want to name as something else, you could do so and explicitly call it out saying -file, right? So here I have not changed the name, so I'll just use the name as DockerFile. And -tag, I'm saying that hey, tag the image once created, and I'm giving the name of the image as TailSpin. Towards the end, I put a dot stating that the image, the Docker file is available in this particular location. So what Docker would do is to build that image layers one on top of the other using the intermediary containers, and then my Docker image is created right here. Awesome. So let's go ahead and use the same host to bring up that container. All right. The command to use to run the container in the host is docker run followed by port 70. I'm asking Docker to open up port 70 in the host, followed by -d saying that hey, run this process as a daemon process, followed by name of the container, and finally the name of the image that is in my host. So the container is created. To just validate it, I can open up localhost and the container is up and running in localhost. Okay. So let me open up the Docker instance that's running just to show you how to observe the containers. So these are the containers that's running in my host, and I can also see the list of images that's in my host. Okay, if I want, I could actually push this TailSpin image to a container repository. It could be an Azure container registry or Docker Hub. Okay. Additionally, if I want to interact inside the Docker container, I need the Docker container ID. So the command is docker ps-a, which provides me the container details. So let's copy the container ID and let's get inside the container. docker execute -it is interactive, provide the container ID followed by sh. So I'm inside the container, I'll just do ls and I'll see the TailSpinSpaceGame project details inside the container. Okay. So let's go back to my whiteboard. So here is where we stopped, right? Andy has built the container image and the image is now ready to be pushed into a repository. Why do we need a repository, right? So here the host contains the container image as of now. If you want the image to be run in multiple hosts, if you want the same container process to run in multiple environment, maybe the on-prem virtual machine or on-prem servers or cloud services, you need to store the container image in a secure repository. In Azure, we have an option which is called Azure Container Registry. Okay, so you can apply RBAC, role-based access control, for any resource or service that's accessing Azure Container Registry to pull the Docker image. Consider that Docker image is a production image, right? So you want to make sure that it's securely stored. And hence you may want to choose Azure Container Registry, which is a private repository for Docker container images. Now, when it comes to deployment environment, we need to ensure that the deployment environment has a Docker runtime. Okay, in Azure we have a couple of options, which is ACI, Azure Container Instance. So these are standalone container instances. So for a single container instance, you can create a group of containers, 1 to 2 or 3 at the max. So what it means is that all the containers would run in the same host, right? Container 1, container 2, and container 3. And all these 3 containers are together called the container groups, and it can talk to each other in localhost. So this is container, Azure Container Instance. Okay. So the second option that we have is web app for containers. Okay. So web app for container is a fully managed service. It's a platform as a service where you can deploy containers and you can scale out containers. The third option is Azure Kubernetes service. So AKS is a managed service again. It's a Kubernetes cluster orchestration platform wherein you can deploy containers, manage multiple containers. Generally, we go for AKS when it comes to microservices. So if you want to know additional details about these services, check out our video in the same channel. My colleague Yas has detailed out all these services and its advantages as well. So with that, I hope you kind of like the video and you got an understanding of a little bit of internals of containers. So thank you for watching my video, and I will see you on another video of Azure Roundup. Thank you.